Glad to have you here today. Our keynote speaker in this afternoon is Bogdan Suceavă. Bogdan is a professor of mathematics at California State University, Fullerton. He received his undergraduate degree in mathematics in 1994 and his master in geometry degree 1995 from the University of Bucharest, and his doctoral degree from Michigan State University with a dissertation of curvature invariants written under Pang-Yang Chen coordinations, 2002. His scholarly publications cover a variety of themes, including differential geometry, metric geometry, history of mathematics, and mathematical education. His works in mathematics is recognized with Mathematical Association of America's 2020 Olia Award for Expository Writing and Romanian Society for Mathematical Sciences 2020 Medal of Honor. Bogdan Suceavă is a member of the department presented by the American Mathematical Society with the 2022 Mathematics Programs That Make a Difference Award. Suceavă is the author of 17 literature volumes, including the novels Coming from Off-Key Time and Miruna, A Tale. 3 of his essays are included in Princeton University Press series, Best Writings on Mathematics. Editor of 3 volumes in the Contemporary Mathematics series with American Mathematical Society. His talk today is about representations of the idea of space and the concept of curvature, from Nicole Oresme to contemporary interpretations. Bogdan, you have the floor.
Well, thank you very much for your invitation. It's a great honor for me, and thank you for this opportunity. It's great pleasure to take you back to the 14th century. So just a brief confirmation, do we see the screen?
Yes, Bogdan.
All right. So let me briefly outline first what I like to do. So I'm going to start looking at the origin of the idea of curvature, where this started, and why it was actually important originally, where is the beginning of the idea. That's why we're going to look at the doctrine of configuration. That's a book written by Nicole Oresme about the mid of the 14th century. And then we're going to compare that work with the beginning of the modern investigations on curvature that's actually starting with Christian Huygens, and the first definition that we're still using today, it's due to Isaac Newton. Then we're going to stop a little bit and contemplate a strange little thing that's in Euler's work, just to get a feeling of how difficult the problem was conceptually. And I'd like to wrap it up with look at the work of Carl Friedrich Gauss and Sophie Germain at the beginning of the 19th century. And I'm interested in the paradigm. I'm interested in the package between a space and the idea of the formation of that space altogether, and how this was viewed in various historical times. And that's going to give us a glimpse of something that's of interest today. Okay, so that's the plan of attack. Hopefully, it's going to be lasting for 55 minutes, but we'll see. So the homework for all of us, it's being outlined first in a paper published in the Monthly by Julian Coolidge back in 1952, where he's writing that the story of curvature is unsatisfactory. And he says that the first writer to give a hint of the definition of curvature was the 14th century writer Nicole Oresme, whose work was called to my attention by Carl Boyer. All right, so we're in 1952, and I would venture to say that it's very likely Julian Coolidge never saw the English translation of Oresme's work, because that was published in 1968 due to the efforts of Marshall Clagett. Carl Boyer definitely saw the Latin version. And that's actually something that was worth investigating in detail. However, Coolidge comments, Oresme conceived the curvature of a circle as inversely proportional to the radius. How did he find this out? Now, this is becoming really interesting because if you're looking at Oresme's background and the amount of mathematical really culture he had, it's interesting to see, because if you talk about deformation, you're actually making the first steps in the realm of differential geometry. But in the 14th century, this is way before calculus. So how was this even possible, and why was this needed? Okay, so what just happened in the late Middle Ages in Western Europe? Major event. There was the so-called recovery of Aristotle, when breaking news. There was once upon a time a great author whose works are not entirely known in Latin, and they were translated slowly from Greek or intermediated from Arabic. And the overall effort was done mainly in Spain. It's about 42 books, and that's perhaps about a third of the original. So we have an idea about other works, but they never made it to us. Now, everything I'm going to say about Oresme should be viewed in the context of the aftermath of making available Aristotle all across Western Europe due to a series of translations. And this went about like the fabrics that were produced in the Islamic world. We have here like an example of a fantastic piece of silk that was nevertheless imported in France and was incorporated into the garment of a bishop. That's what just happens with the translations. They will be coming from Spain, and they will be used in the texture of Western European efforts. Now, what is known before that is that the categories and on interpretation were available due to earlier translations. They were coming from early medieval era. And that's important to know because it is very likely we had more copies of them all across Western Europe. For example, let's call on the first witness. St. Augustin describes in the Confessions how he was underwhelmed by a reading of categories when he was 20. Then, what a daring project. Boetius planned to translate into Latin and comment upon the whole Aristotelian corpus and reconcile it with Plato. And that was daring. He didn't have time to engage it too much. One little detail, it's hidden in Aristotle. The idea of continuous measure. Continuous measure, that's not something that, I mean, how do we think about that in medieval terms? Because as a mathematician, if when you hear continuity, you already have a good frame to think about. It's something that was clarified during the modernist transformation of mathematics at the end of the 19th century, but originates in the work of Augustin Cauchy. So that's a very important concept. Let's take a look. So if you're going into categories, Aristotle is distinguishing between discrete and continuous quantities. Okay, I believe the word continuous appears about 7 times, if I'm not mistaken. And at some point, time is said to be continuous. He's mentioning among the continuous quantities, line, superficies, body, and line is continuous if you flip one page further. And then place, that is the space. I was mentioning the problem of space. Space is continuous. All right, we got this. So definitely the claim that the idea of continuous measure appears in Aristotle, that's true. It's in the text. So claim number 1, the fact that Aristotle discussed continuous things attracts the attention of Nicole Oresme. And it happened in the 14th century, perhaps in the worst possible time to do mathematics, if anybody was interested in that. And let me try to date it. And I'm going to pick up a pick with Notre Dame before the fire. So why is this important? Because when Nicole Oresme made it to Paris, they were still building the last details of the exterior of Notre Dame. And the content I'm going to talk about is coming from this historical period. Now, one little detail, if you're looking at the exterior walls, you're seeing here these strengthening devices that are called the flying buttresses. Their role is to actually take the weight of the walls and send them into the ground according to the direction of each one of these arches. This is a fantastic idea, and it shows a good understanding of the idea of tension. Okay, so all these constructions have been actually designed, made, understood way before the theoretical understanding of the concepts that are calculus supported. Like if you're thinking in terms of tension, the rigid structures, that was done later. This is civil engineering in the 19th century. But the guild's craft back in the 14th century was able to do that, nevertheless. Okay. So who defined first the concept of curvature and how was it used for the first time? And if I'm allowed to overshare here, I actually this problem was I picked it up from a survey that my advisor Bang Chen wrote back in 2000. It was a survey that was published in a volume, a handbook of differential geometry, and the survey was titled Romanian Manifolds. And right at the beginning, it says that the concept of curvature appears first at Nicole Oresme, and that he was a clerical scholar. And of course, when I read it first, it was like, what is a monk doing with curvature? And I asked my advisor, and he told me, it's the definition definitely appears there, but it's not entirely clear why he needed it. Well, I found it, it's a very interesting problem. Why does a theologian in the 14th century need curvature? I mean, why do you care about that? We'll clarify the mystery in a few minutes. So that's official. The first definition appears in a book that we're gonna call briefly De Configurationibus, and we know when it was written, between 1351 and 1355. The chronology was settled by Claudia Kren, who back in the days when she wrote her doctoral thesis at University of Wisconsin in Madison, she made a fantastic effort to pretty much keep the track of what Nicole Oresme was writing in different periods of his life. And I'm going to explain this later on. The chronology is confirmed by Marshall Clagett. So we have an interval of 4 years when he could have written this treatise. Now, it's a work that we can't explain. If you're looking at there's this huge handbook of sources in mathematical history that Dirk Struik, who taught history of math at MIT, wrote. Dirk Struik is suggesting that Nicole Oresme it's a very special case in the history of math. He's somebody who's really out of his time and doing very different things and very creatively constructing concepts. And I believe we're going to have the proof very soon. So here's the definition. Consider the circles with radii B and AC. If the radius AB is twice the radius AC, then the curvature of the smaller circle is double the curvature of the larger circle, and so on for all the other proportions of the curvature. Okay, as clear as it gets. Now, if it was only for that, you could say, perhaps he took it from elsewhere. And honestly, he could very well have taken it from elsewhere. We don't have a proof. We don't know. But the interesting part is, what's he going to do with it? because in the doctrine of configurations, as we're going to see, this is needed. So the way he has taken this idea and builds a theory on it, it's impressive. So let's play the following game. It's just an intellectual game. Let's try to keep the standards very high. Let's imagine that we're looking at the old text from the 14th century, and we're going to try to expect from it some level of accuracy as we would expect nowadays from a text written today. And you're going to say, hey, this is not fair. This is not really fair. But the surprise is that, this is holding critique. So how do we give modern definitions? We like to have things very clear, all right? So let's see. I'm going to try to define curvature as for a calculus class. So suppose I'm driving my car, okay? And suppose this is the wheel. This is the wheel. Suppose I'm driving with constant speed, and I'm going to turn the wheel. What happens? The trajectory alters. So let's keep track of the forward direction. This is the forward direction. When I'm going to turn the wheel, this direction changes. Would it be decent to say that the trajectory curved as much as I turn the wheel? So how would I do that? It's like I'm talking about the rate of change of the direction with respect to the distance I have been driving through as I turn the wheel. All right, that's exactly the calculus definition. Because if you have a curve, t is the unit tangent vector, that means forward, and ds represents the arc length. So it's the rate of change of the unit tangent vector with respect to the arc length. You should take the magnitude, and that's the curvature. Okay, this is how we present it to engineering classes, and if you match it with the original definition, it's going to take it into the same place. And of course, what's missing in the 14th century, and we'll see that this is something that Nicole Oresme can't overcome, the idea of rate of change. He couldn't possibly have seen anything like that, because that's something that appears when calculus was born. That's the end of the 17th century. So Nicole Oresme is approaching calculus concept with tools that were prior to our understanding of the rate of change. All right. Back to Coolidge's question. Oresme conceived the curvature of a circle as inversely proportional to the radius. How did he find this out? Okay, can I venture myself into a hypothesis? I'm going to believe Oresme by reading Aristotle and taking, and later on, teaching classes at the Collège de Navarre. So that's not University of Paris. That's the poorer cousin in Paris. That's Collège de Navarre. So, but the key fact, the punchline, is that Oresme needed the concept of curvitas for his doctrine of configurations. So, did you ever hear about doctrine of configurations? Do you know what this is? Don't you worry, because this is a theory that did not survive the 14th century. It never made it. It's not a theory that was like successful in terms of impact. It's a theory that could have been highly useful if the historical context was different. By the way, when was the Black Death? That terrifying plague that devastated regions of Europe. That was like 1346 to 1352. So in that interval of time, Nicole Oresme was writing a doctrine of configurations. That's why I said, it couldn't have been a worse time for anything that would seemingly look like, research. So Nicole Oresme was born around 1320 in a village called Almagny. That's in the Greater Cayenne area. Today it's called Fleury-sur-Orne. Name of the place was changed in 1914. You couldn't have a village called Almagny, right? And as far as I'm aware, some researchers are actually indicating that Nicole Oresme was born in 1323. It's still up to debate. I'm not entirely sure if we'll ever know finally when he was born. But what we do know is that he came from Normandy to Paris sometime prior to 1342. Maybe he was 18. Worst case scenario, he was 22. Originally to study arts. And then he studied theology. Let's explain this. So if you're going to Collège de Navarre, you would have a fellowship. You are like the brightest in a group of students, and you're going to get a fellowship. That's called a bursar. So he was supported as a bursar up to about the age of 36. Now, what does it mean study arts? It's very likely it was looking like, studying quadrivium and all the classical arts, and that was the classical training. And for theology, that's quite interesting because the priests at that time, they were expected also to have a little bit of understanding of financial matters to balance the budget of a church. So that was enough to study proportions and a little bit of algebra. Good for his background. When he was studying arts, he also had the chance to see nothing less than Euclid's geometry. We have proof that he did see that. Okay. Now, Collège de Navarre, how was this? We're looking at something that was demolished in 1811. That was on the left bank of La Seine. And it was established by a donation of the Queen's jewels at the beginning of the 14th century. It was a pretty crowded place with a cathedral and a library. And I bet the only quiet place in this complex was the library. So Oresme studied arts before 1342, earning the degree of Magister Artium. That means a little bit of algebra up to proportions. We don't yet have the notations like in François Viet style, but sufficient for him to come up with, later on, with something really impressive. This is the first author who ever proved that the harmonic series is divergent. The proof was lost and rediscovered 400 years later. Dirk Struik actually is confirming, this is the first time when somebody is proving that the harmonic series diverges. If it was only for that, he would be a special case in the history of math. But there is more. So he's a major in theology. He's getting a doctorate in theology. That's going to open up a lot of doors for him. And then there is the other thing. The habit at Collège de Navarre, where they were learning by rote. So they were taking some text and pretty much memorizing the texts. That's actually, just imagine somebody with brilliant intelligence having to memorize a fragment of Aristotle. Sooner or later, he's going to make connections, notice things. Pretty much seeing something like continuous, time is continuous, space is continuous. What was there? He was scriptures, he was the fathers of the church, he was, and then Aristotle. That was his education. Now, he did have, I was mentioning that he's not at Université de Paris, he's actually at the College of Navarre, but he had outstanding educators there, Jean Buridan and Albert of Saxony. And while he was there, he wrote the Proportionibus, which is the algebra-like work among the corpus of books written by Oresme. And he's leaving also a few documents that have to do with ideas in the celestial mechanics. Now, Oresme happened to have been of the opinion that the Earth is not flat, it's round. And the universe, it's in the middle of 9 spheres, the celestial spheres. And the sun, I forgot, it's like the 5th of the 6th sphere. And anyways, the sun is closer to the Earth than the planet Mars, and so on. It's a model that I don't think it survived 14th century. So what did he write? Here's interesting. We're going to look at the works. By the way, this is not everything he wrote. I just selected a few. He had a bunch of works that could be classified as mathematical, and a bunch of works that could be viewed as related to Aristotle. So we have some comments about Euclid's geometry. They're not very deep. I mean, if you try to compare his work with the comments from the late Roman period, he's not winning the battle. It's interesting when he's commenting on Aristotle's De Anima, because if you remember, Aristotle was actually banned twice at Université de Paris, and every time it happened for De Anima, every time they were, earlier, when they were looking at the content, there was a doctrinal problem with Aristotle. And the fact that Oresme is commenting on De Anima, that's interesting. Is the next generation after the banning was over. Questions de Sfera, I think I mentioned about the celestial model. And then he's really an expert in Aristotle. That's what we're looking at. In the next decade, De Configurationibus, which is the big deal, and the algebra-like work I mentioned. Now, we're looking at 1360, and I'm going to draw a line. 1360, it's about the time when he's turning 40, and the matters change. We'll discuss in a sec. So in this interval, we know precisely that there is this work that's somehow different. It's a book on currencies. He started as looking at the accounting work, and this work, actually, this De Moneta, will circulate for the next 200 years across Europe. And one of the readers that we know was Copernicus. So Orem's work is quite diverse. So he's remaining master of the college until 1361, when something happens. He's forced to resign. I don't know if we have all the political details about what happened there, but it looks like somebody wanted him out of Paris. It was really bad that he stays in Paris, and I'll explain soon what happened. So he's becoming, he's promoted. Suddenly he's kind of kicked out, but promoted away from Paris to Rouen, where he's becoming a canon of the cathedral and then the dean. He's doing fine, but away from Paris. In the second period of his creative life, he's writing against astrologers. Livre de Divination, he has a problem with astrology. He has a problem with horoscopes. And then this new treaty on the sphere, it's actually, by the way, I don't have a misspelling there. That's Middle Age French. That's how it was written. He's starting to write in French, like vernacular French of his time. So let's take a look. How many Orem do we have? We have 3. There is the independent thinker and researcher. There is the Latin scholar. And then later on, after 1360, is the writer in vernacular French who's interested in reaching large audiences. We're dealing with 3 different kinds of contributions. And I believe this is the last work, Le Livre du Ciel et du Monde. And the fact that he was in Rouen doesn't mean at all that he was in a marginal position. Not at all. He was still close to the king. There was, extensive interactions between him and the king, and that was actually the problem, the political problem that he had to face, because there was serious competition of who should be the king's chaplain, or the king's, even worse, the king's confessor. Discussing with the king, that was a very powerful position. So he had friends, and not only friends. In 1377, with the support of the king, Nicole Oresme becomes Bishop of Lisieux. His health is declining, and he's dying in 1382. So this is the story of his life, and we can see here the periods and the way the whole matter evolved. Now, the king. It's actually one of the most intelligent politicians ever, and here is why. He had a couple of moments in his career when he had everything against him, and he turned the tide. This is the 100 Years' War, and Charles Le Sage had at some moment, the whole city of Paris against him, while the English army was near Paris, and he turned the tide. Who was for him? A couple of advisors, a couple of good politicians around him, a couple of clerics who were still faithful to the crown of France, and he played the game in a way that he won. Save the crown, save the House of Valois possessions. That was a very difficult game to play. So Oresme became the king's confessor and advisor. And I'm going to say that his political influence is difficult to assess, really. I wish I was a fly on the wall to see what these guys were having conversations about, because I'm pretty sure that Oresme was questioning some of his advisors, especially the ones who were, believing in soothsayers, in predicting the future, in reading the future in the stars. If they were going that way, pretty sure Nicole Oresme was advising against them, and that's why the enemies. And it's not entirely clear whether the king was listening to his confessor. So it's very clear. So the reason why we're looking into all these details is that the way he's writing has to do with the context. It has to do with the whole situation that we have in Paris at that time. So who was Nicole Oresme writing for? For the king, definitely. For the intelligent people around the king, they were educated scholars in the service of the crown. For the clerical audiences, and there was, that fantastic audience at Université de Paris, the School of Medicine. That's the audience. Okay, so in order to tell them something that they could pick up from all these texts, you should make references to things they know. You refer to the Bible. You refer to things that they know. They have in like a common ground to let the arguments get across. Now, we don't know exactly before 1370 he became the king's chaplain. We don't have like an official document, but definitely it looks like, as early as 1361, this connection existed. Okay, and then something really amazing happens. It's very clear that Oresme was advertising for Aristotle, and the king wants to read Aristotle. But the king is not as fluent in Latin as Oresme. So he's commissioning the translations. So Aristotle's ethics, politics are translated, and the economics. But see, nowadays we know that the economics may have been written by somebody else, not by Aristotle. So anyways, at that time, the translations made it. Translations of what? Okay, so let's take a look. So we have the original Greek in Aristotle, made it into Latin, and from the Latin is translated into vernacular French of the 14th century. And that's the language in which we, for example, have the poetry of Christine de Pizan. This is, I'm looking here at an edition that's issued by Gallimard in 2019. And Gallimard says that this is a bilingual edition. So these are two different languages. Oresme's translations nowadays, they sound different. And you can actually measure, you can write a doctoral thesis by looking how much the original text from the original Greek transformed while making it into vernacular French. Let's say the least that there have been some inaccuracies in all these translations, especially some parts of the text were intermediate from Arabic. All right, let's get to the main idea. What's going on with De Configurationibus? How do we think about it? So it's a work made of 3 parts. Part 1. You know what? I'm gonna give you one image. If you remember the way you have been taught about graphs of functions for the first time, maybe it was in the 7th grade, in the 8th grade, or maybe high school, graphs of functions. The very fact that you can graph a function, I don't think we nowadays reflect too much about it. But we are in a historical period where there was nothing like graphs of functions. So those configurations should be thought as graphs of functions. However, we don't have anything like functions in Nicole Oresme. Because what's a function in modern language now? We have a domain, we have a range, and the law of correspondence. To every element from the domain, one element from the range. Okay? If you're doing the graph, there is something called the vertical line test. If a vertical line crosses the graph only once, that's a function. If you have like a circle and it crosses twice, that's not a function, that's a relation. Well, we have nothing like this in ORM. We have just configurations. And configuration should be thought like graphs of functions. So what we have here, it's theory, it's an early theory of graphs of functions without functions and 300 years before calculus. Okay, what's going on here? Here's the strategy. So Oresme is seeing around him a lot of superstition, a lot of beliefs in astrologers, and he's adopting an interesting strategy. He's saying, how about if we develop a theory that's mathematical to convince everybody that these guys are wrong? Like more math to settle the matter. All right. Is this going to work? Let's see. He's applying his doctrine, which is a theory of graphing functions, to qualities. What are these qualities? Are they like models of things that happened in real life? We have to be very careful with the word model, because for mathematical modeling, you need the paradigm of the scientific method as it was developed in at the beginning of the 17th century. Okay, we are way before that. So we don't have the scientific method. We don't know how to collect data to turn it into a model. But he is giving us examples, things that could be mathematical models. So those entities that he's using here are potential mathematical models. So while discussing these elements, he is suggesting that the theory could explain in a unitary framework physical and psychological phenomena. He's putting them all under the same umbrella. So that's the doctrine. All right, in the second part, Oresme describes how graphical representation can be applied to entities that are successive, in particular to motion. Then he's concluding that some of these applications could be done on psychological phenomena, in particular to perceptions that are described as magic. All right, but let's see. Suppose I'm an observer in good faith of a certain phenomenon. I'm seeing it. My perceptions are deforming without me knowing what I'm seeing. I said deforming. So I'm going to write or retell what I saw. When I'm performing this process, I'm deforming again. And then the person who's hearing it is replicating the same process of deformation. After several iterations, we don't have any more descriptions of the accurate observation that happened initially. So that's why he needed deformation, for ethical reasons. He wanted to describe how the truth and how statements, how descriptions are deformed. Okay, so he's not interested in civil engineering, architecture, and measuring tension and so on. Nothing like that. The motivation is the ethical grounds of psychology. Okay, so what are we expected to understand from this? Well, all these people who believe in astrology, they're in good faith. They're in good faith. They're good people. But they have been misled by their perceptions, by their expectations, by the way they model their perceptions. So everybody is off the hook, but the theory is false. This is where we're going with that. Finally, in the last part, and this is the mind-blowing piece, Warren describes external geometrical figures used to represent qualities and motions. And at some point, he has comparing areas. Comparing areas like what? To compare if certain qualities are, if one is greater than the other. I mean, comparing areas, this rings a bell. Because when Carl Friedrich Gauss defined curvature, he was with comparing areas. It was with comparing areas and the limiting process to get to the modern definition of curvature for surfaces. Nicole Oresme, he's comparing areas in the third part of the Configurationibus. He's saying it. There is no quantification whatsoever. He can't do the numbers. But the idea is there. Now, this is really something else because there's a lot of good geometric intuition here for models that could have been more if there was a better support from the quantification side, both algebraic and statistics. So he's writing right at the beginning. He's going like, every measurable thing except numbers is imagined in the manner of continuous quantity. Aristotle. Then he argues that qualities can be figured. So he's talking about this function-like concept that he doesn't really define as we wish to see a modern definition, but definitely it can be figured. By the way, the statues I have up there are from the cathedral in Rouen. So I bet he saw these statues. And he says, we know that from Aristotle. So basically, why not believing him? I think he's indicating the main authority at that time, and I believe he's citing what he knew, and he's really kind of continuing Aristotle in a certain way. So I believe this conversation that we have here it's in the continuation of the paradigm of the recovery of Aristotle. That from this analysis, an analysis of curvature came out. That's surprising. Now, interesting. We're still in part one in the Configurationibus. Oresme talks about uniform versus deformed qualities. And then he's talking about simple deformity, which is of two kinds, simple and composite, and so on. What is a uniform quantity? I'm gonna have to dance. Here it is. Oh, is this a line? And simple deformity is what? The modern language would be like a curve in general position. He doesn't have the language of the theory of curves. He doesn't do that. He's making up the theory, making up the names. He's talking about curves. And then, of course, if he has graphs, he needs to have curves and a good understanding of curves. And now he starts to compare the deformation of curves because they support his models. Okay? And he comes up at some point with 4 kinds of graphs. And that's an early conversation on convexity and concavity, and surprise, surprise, he's using these words. Now, convexity. This is definitely related to the second derivative, if we speak calculus, okay? He doesn't have rate of change, he doesn't know what the second derivative is, but the classification works. The graphs are described. And not only that, he's moving over and discusses surface quality. So he's trying to do calculus with several variables without really having the data. And that's the context in which that definition that I started with and that Julian Coolidge heard from Karl Boyer was stated. Oresme needed curvature for his doctrine. Now, a particular case of entity is curvature. So now, see, the curvature, the deformation itself is becoming something that can be graphed. And it has both extension and intensity. Now, if you want to put it on two axes, extension and intensity is, extension is the x-axis, intensity is the height. But think like this, back to the driving story. Extension is, for how long, and intensity for how much I turn. He's getting everything right. And this paragraph, with your permission, I'm just going to read it in Marshall Claggett's translation, slowly. We do not know with what, or with regard to what, the intensity of curvature is measured. For now, it appears to me that there are only two possible ways to speak of the measure of curvature. The first is that the increasing curvature is a function of its departure from straightness. So the very fact that the graph is curving as much as you are deforming, it's a departure from rectilinearity. He's saying it. That is, of its distance from straightness. This is to be measured by the quantity of the angle constituted of a straight line and a curve. That is the angle of contingence, or perhaps another angle, also constructed from a straight line and the curve. You're reading this fragment and it's going like, oh no, this makes perfect sense, because the modern concept is that of turning angle. How much I turn the wheel is how much I curve. Now, in modern geometry, we have the rate of change of the turning angle with respect to the arc length is curvature, and you can take this as a definition if you don't like the other definition I started with. But nevertheless, if you're looking at the fragment from Oresme, that's correct. He doesn't have a proof. It's just feeling, it's just intuition. But that works, and it works for simple deformities. Therefore, that concept of curvature is extended to curves. Okay, the proof is right here. Now, the text was looking about like that. So what you have inside the text, you have these drawings, these graphs that are actually showing the various ways of, and he's using, as you can see, convexity, concavity, all the words are in, like this was a modern calculus treatise. And then, on the deformity of joys, one ought to speak in the same way concerning a joy or a pleasure, which I suppose to be a certain quality, extended in time and intended in degree. So, the intensity of joy as I'm drinking my coffee. Here's the graph. Okay, so you can graph, it's graphing joy. Or you can do that with subjective perceptions. If you're going to the doctor's office and the doctor is asking, well, on a scale between 0 and 10, how much does this hurt? And you're saying, well, this is a 6, and then the doctor knows what to prescribe. So subjective perceptions as functions, this is very difficult to model. It's very difficult, even today. I mean, if the modern applied mathematics is challenged to graph subjective perceptions, that's a serious issue. Because how do you measure? And Nicole Oresme is using this as examples. And he's putting this in the same package with displacement, curvature, and all the other examples he's using. So the examples are from mechanics, physics, if you like, the physics of movement together with psychology. Put them all together and build up a theory of functions for it. All of that based on Aristotle and a little bit of reading of accounting and Euclid. How about that? Now, this is a manuscript, one of the earliest that we have. It's in a library in Florence. And here we can see something really particular. All those drawings, the convexity and concavity, they're taken aside from the text and moved on a lateral column. But then the interesting part is this drawing at the bottom. By the way, this is non-trivial. I mean, this is really somebody, at least the copyist, who has seen a little bit of geometry. So, here's a surprise. Surprise, surprise. Every deformed curvature is deformed in a way different from that in which any other quality of another kind could be, and so it is deformed with a strange, marvelous, diverse kind of deformity. Okay, let's cut to the chase. First of all, he's not distinguishing between curve and curvature. For him, both of them are curvitas. So every deformed curvature is for any curve in general position. The shape is unique. So why do I care about such things? Because you see, if you have a device like this that's using the unique pattern with which all of us were born, pattern recognition is actually relying on something that we call the fundamental theorem of curves. And that's something that's incorporated in modern technology all over the place. It says this, that for a curve in 3D, if given the curvature and torsion, then the curve is uniquely determined up to rigid motions. Now, for planar curves, you don't need torsion, just the curvature. So that curvitas determines the curve. I mean, to prove it, you do need differential equations, and that's a concept developed after the Bernoullis. Okay, we are here very early, and Oresme doesn't give any proof. He's just concluding a chapter with this statement, which is in his doctrine equivalent to the fundamental theorem of curves. Back to the initial joke. What was the monk doing here? That's quite impressive. Now, curvature and torsion are different shaping variants. Torsion was actually born in 1805. To handle them properly, you need Frenet-Serre equations. That are the differential equations that characterize the geometry of differential curves, proved after 1847. So with that, it's official. So Nicole Oresme was born 5 centuries earlier. He's approaching these questions. He doesn't have the tools, but he has the intuition. So to summarize, a 14th century scholar, just on this component, gave a correct definition for curvature of planar curves, because now, after examining his work, I start to believe it was his contribution. I think if he imagined all this other stuff, I think he was able to imagine that kappa equals 1 over r. I think that makes perfect sense. And then try to apply curvature to understand the behavior of real life phenomena. So that's really something that's anticipating mathematical modeling in a very early stages. He's producing a statement that anticipates the fundamental theorem of curves in the plane. That's highly non-trivial. And now in his doctrine happens this coupling. The configurations are discussed in a package with deformations. But this is exactly the package that Bernard Riemann used in 1854, where he introduced Mannigfaltigkeit. Because manifold came with the idea of curvature extended to n-folds, as he was writing. But Oresme is doing the same. He has the object, has the graph, and he has the way of describing his deformation. The package is there. The context, when he's picking up all these examples, we do know that the staff at Collège de Navarre, the priests, the theologians have been summoned to help during the Black Death. I mean, maybe having to do the last rites, and it was a very difficult time. And you can, when you read, you can see what was his experiences. You know, he's talking about the intensity of perceptions. He's writing about the intensity of pain. So let's put it in a frame and let's see what happened in the same time. So in that historical period, you know, Chaucer was a kid in London. Boccaccio wrote the Decameron, so that's about the same time. Petrarch was coming up with an expression like Dark Age, and he was working in Florence. And we do have a qualified witness of that historical period in France. That's Jean Froissart, who wrote Chronicles. So in the same time, with all these creations, we have the Configurationibus. So why was his work forgotten? It might have to do with the institution. Collège de Navarre wasn't really teaching the stuff that we're producing. I mean, the research done there was not really taught there. That's one thing. Secondly, I'm wondering how many people in that particular historical period were actually understanding the doctrine. And his work was less understood and borderline forgotten. Later authors like Christian Huygens, who came up with the isochrone curves later on, and Isaac Newton, who came up with the first definition of curvature, they didn't need the doctrine of configurations. That was a whole different language. Everything that happened after 1600s was built on a different paradigm. So Orem's mathematical texts were forgotten. So that by 1952, when Julian Coolidge wrote, only a few specialists knew of their existence. Now, this story is written in a paper with Isabel Serrano. The paper is freely available on the web, courtesy of American Math Society. The title is A Medieval Mystery, Nicole Oresme's Concept of Curvitas. Isabel Serrano is today pursuing a doctoral program in statistical biology at UC Berkeley. And there is this other work that was published a few years ago with the memoirs of the scientific sections of the Romanian Academy, where we invited to join us in our investigation Anael Verdugo, who's a very good applied mathematician, to help us understand what Orem was saying. And we ended up with investigating pleasure, imagination, fear, and joy as applied themes in De Configurationibus. I think I mentioned the idea. But let's see, why couldn't Orem do more? 1671, Isaac Newton is defining curvature. The way it works, it was like this. So officially, that's the beginning of the modern concept. Newton writes that he's extending, I mean, very faithful to the old geometry, he's extending the analytical art. That means whatever was developed after Descartes' heritage. And to this end, says Newton, I thought it not amiss for the sake of young students in this science to draw up the following treatise, wherein I have endeavored to enlarge the boundaries of analytics and to make some improvements in the doctrine of curved lines. He's building the modern theory of curves, because the geometric locus of centers of curvature, that's the evolute that's coming from Newton. And the idea is this: take a curve, take a point on the curve, and you're going to need the tangent line to it. Tangent line, about like this. Now, to do the tangent line, you need the rate of change that Orem couldn't have. That's calculus, okay? Now, perpendicular to the tangent, you're going to have a line that we're going to call normal. And with the center on the normal, you draw a circle. If the circle is too close, maybe about like here, then expand it until you're going to get a last circle, after which the region enclosed by the circle is exceeding the region of the plane enclosed by the curve. Then this is going to be called the limiting circle. And this limiting circle is the circle of curvature. So there's a definition how it comes from Newton. So what you need is the rate of change, you need the idea of limit. Those were available courtesy of, Leibniz and Newton, 17th century, but they were not available in the 14th century. So Orem did pretty much as anyone in the 14th century could have ever hoped to do. But he was bounded by his time, by his paradigm, by the context he was working on. And then how about extending this to surfaces? Because if you're looking at the original Orem's attempt, that was actually an attempt to extend it to surfaces. Well, how about the following idea? So imagine I'm playing around with a surface that looks like the monkey saddle I have on the screen, all right? Suppose I'm trying to approximate this with a sphere. suppose I have a basketball that I'm trying to place on the saddle. Okay, on which side would I put it? Do I put it on the top, or should I approximate the surface from underneath? That is the question. And when Euler thought about defining curvature for surfaces in much cited work, he said this is not possible. By the way, this paper is the paper that Gaspard Monge gave to Jean-Baptiste Meunier to study, and Meunier extended Euler's theorem based on a problem given by Monge, inspired by this paper. So what do we read there? So we read the following. Pour connaître la courbure de la ligne courbe, la détermination du rayon osculateur en fournit la plus juste mesure en nous présentant pour chaque point de la courbe un cercle dont la courbure est précisément la même. So that's fine. It's Newton. But then the next sentence is the problem. Mais quand on demande la courbure d'une surface, la question est fort équivoque et point de tout susceptible d'une réponse absolue, comme dans le cas précédent. So Euler was actually confused by surfaces that, today we call them hyperbolic surfaces. If this was easy, then why Euler was confused? And I don't know, I think I'm exceeding my time allowance. Marius, how am I doing?
You are okay, 4 minutes.
In 4 minutes, I can bring it to contemporary times. All right, let's say this. So one of the figures that was responsible for Euler's confusion was the catenoid, which was known in 1763. So the way we think about nowadays is what's an elliptical surface and what's a hyperbolic surface. The way we look at is like this. So suppose my jacket is the surface, and that's going to be the tangent plane at a point. Pick up this point and put the tangent plane to it. If the tangent plane is keeping the surface on one single side, then that's an elliptical surface. All right, so for a surface like the catenoid, let's say I'm picking up a point on the side here. If I draw the tangent plane through that point, the surface is crossing through the tangent plane. So that's hyperbolic. So you could do those approximations in the case of elliptical surfaces, but you can play the same game for hyperbolic surfaces. So a different definition would be needed. And that was about to come only in 1827 due to Gauss. And this was paired by an investigation by Sophie Germain in 1831, because you're going to need two measures. You need the classical curvature, Gaussian curvature, and the mean curvature that was introduced by Sophie Germain. These are the two of our invariants. That was not easy to come up with, because if you're looking at from, what was that, 1763 to 1827, that's 6 decades, that's 2 generations. Took a long time. And when Gauss wrote Disquisitiones, he's very kind and polite, and you know what he does? He's not citing Euler. He's not pointing out that Euler skipped something, and nothing like that. He is very kind and just not citing. So I promised you this idea of what's inspiring here for contemporary research. Well, I'm going to tell you. Is this. Sophie Germain, she wrote about la loi de distribution des courbures. So it's important to understand whenever you have a geometric object, how the deformation is distributed around the point. That's something that can be pursued today. And it doesn't matter what kind of object do you have, because geometry is changing shape and changing the objects of investigation. Originally it was with surfaces, but later on became with manifolds, and in the last 2 decades we have new geometric objects, from soliton to orbifolds to varifolds, and every time one can think about, okay, what is the measure and how do I study the way it changes around the point? One can think in these terms and investigate, maxima, minima. That's a paradigm that actually can be pursued from the origins until today. It's a legit problem. If you give me 3 more hours, I can.
Thank you, Bogdan. Thank you. It was very interesting, and we already have a question from Rodica Croitor, please.
Thank you, Augustin, and thank you, Professor Suceavă, for your very interesting and well provocative presentation. So first, because you presented here a part of OREM contribution that has to deal with writing in stars, astrology, sorcery, because the 2nd October is a day of Saint Cyprian, Cyprianus, the great sorcerer of the Roman Empire, who became after that very faithful Christian and died for his first faith. But this was a joke for the beginning. As a matter of fact, it's very regrettable that many scientists who succeeded, who came after OREM, didn't enjoy his discoveries, like Newton, for example, and Kant. I have seen that Kant never cited him. And in regard to Kant, I want to ask you a question, because you spoke of the idea of space, of continuous space. Then, if the space is continuous, like in Kant, if there are not breaks in space, there are no void space, that he doesn't allow OREM the void space, isn't it? He speaks of the void space, the empty space. Kant, was tempted due to his metaphysical temptations, but finally he decided that we can speak of it, that the space is not that his term, that the space is continuous, but we understand that when he says that are not intervals between parts of time and space, mainly in space, there are no void space, so nothing between them.
So
my question, as a matter of fact, is Kant. Is OREM, as a matter of fact, because we are going too far from the Middle Ages to the modern times, and in the condition where the work of OREM was not very known by the scientists of the later centuries.
So, Professor Rodica Croitor, thank you very much for the question, and I have to admit I anticipated it. So, can I go back on the slides? So, actually, there are two paradigms that they would be clashing in the early 19th centuries. So it was in the Critique to Pure Reason.
Yeah.
You read is that math and physics are two sciences in which reason yields theoretical knowledge. That is, math and physics have to determine their objects a priori.
Yeah.
And I believe Kant means by a priori that is absolutely independent of all experience. And that space is a necessary representation underlying all intuitions, what lies outside us, right? We cannot imagine the absence of space, only space empty of objects.
Yes.
All right. In consequence, geometric propositions can only be derived from intuition, and not from concepts alone, and that the derivation is a priori. This was the dominant viewpoint in several European universities, and actually, the interesting part is that Carl Friedrich Gauss did not publish his work because of this belief. When Farkas Bolyai sent to Gauss János Bolyai's appendix, the Tantamen, Gauss wrote back to praise it with amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years. Now, that dates back to 1795, and that's before Gauss wrote Acta Arithmetica, right? So we believe Gauss. We tend to believe, I mean, Gauss didn't lie. He was thinking about this for a long time. So the issue is the following. Gauss did not want to go against the paradigm of, can we perceive hyperbolic space? Can we perceive a world where our intuition is not really coming from there? So this was a clash of vision between the paradigm developed by Kant and adopted by many scholars in Europe at the time, and the very idea of geometry as it was developed by Kant. So you are right to the point. This was one of the most interesting challenges and clash of paradigms that ever existed in the history of geometry. And there is this wonderful monograph written by Jeremy Gray titled like this: "Worlds Out of Nothing," and that's actually something coming from János Bolyai. János Bolyai said, "It's like creating a world out of nothing." Can you create a world out of nothing just by stating a few principles and building up that geometry that's against your intuition, but satisfies certain rules that make perfect logical sense? And the short answer is yes. Otherwise, I would be without a job. You know, geometry exists, and there was this difference of paradigm, and that's extremely interesting to follow and to look at the different visions and how Kant's philosophy is actually interfering, and competing with the developments in geometry. That's absolutely beautiful. I'm a great fan of Jeremy Gray, and I learned this trick from him. Like, you know, just looking at the sources and see exactly and comparing the stuff. Thank you for the question. It's
yes, thank you as well. But Kant has many interesting assertions. Some of them are anticipating modern discoveries in mathematics and mainly in physics. He has, in the Critique of Pure Reason, mainly, and after that in Mathematische, Metaphysische Anfangsgründe der Naturwissenschaften, metaphysical foundations of natural science, because physics was named after that period, and mainly in Opus Posthumum, that space, but not formulated exactly, as there is no space and the time, the multifunctionality of this framework in which we used to know. We put our data in order to know in space and time. It's a frame for knowledge, space and time, as a matter of fact, and an intuitive one, given by intuition. But there is no, Kant's problem is that he anticipates that it's not only a space at the time. There are many possibilities for this. But when it's not stated explicitly, we can just guess it, not to rely on it as a firm assertion. So thank you very much.
No, thank you for raising this issue, because I'm absolutely sure he was. If you're looking at that very important philosophical system that's pretty much pushed the whole European thinking ahead, actually interacted with the history of geometry at least 3 times. First, it was the fact that convinced Gauss to elaborate more on Disquisitiones. I believe that document was in the works for quite a few years. Secondly, there was something else happening in 1854 when Bernard Riemann was about to defend his habilitation, the topic that Gauss assigned him was related to foundations of geometry. And Bernard Riemann's construction was actually a response to, and the way it was written, if you're looking at the document, there's no equations in it. It was written to be presented in front of an audience of philosophers. And that construction is actually done bearing in mind the paradigm that we discussed. So it was perhaps the most important talk in the history of mathematics, was actually clarifying the idea of representations of space.
Yeah.
And all this was done in a constructive way.
Yeah.
Well, that's the idea of constructing, atlases. Riemann is calling them kvantas, and that was done in that given framework. And then there is the double piece that's in 1872, when Felix Klein is writing the Erlangen program. From the first paragraph, he's starting with that different ways of thinking or discussing about space. And he says, the mathematician is not concerned with the philosophical approach of space. He's actually distinguishing the construction that's done in the Erlangen program from the construction that's done on the realm of philosophy. So after 1872, I believe we are discussing about different things. But, respecting that important framework of conversation that started after 1787, that's extremely important. That's extremely important. But from the standpoint of geometry, this was the evolution of ideas. And now, if we're looking originally, the original problem of what is space, that's actually coming from Plato, from Timaeus. That's a fragment that Bertrand Russell commented and said Plato is actually classifying natures in three kinds, and the third kind is space, and he's describing what he believes in space is, and there is nothing about deformations there. It's a structure that we imagine beholding like in a dream and so on, because it's out of our perceptions. And Bertrand Russell says, Plato, if he would read what Immanuel Kant said, he would be very happy. These are different paradigms. And for the mathematician, it's a very practical problem. The practical problem is this. Suppose I have an abstract space, and wishful thinking, I would like to move my calculus tools on that abstract space and do calculus there. That's the wish. I would like to have everything like the analytic plane, and if possible, I would like to take derivatives. That's the hidden agenda. And it might happen that some of these abstract spaces, they're really challenging my intuition. No worries, I can do calculus, then I'm happy. So that's the way it works. There are different paradigms, and for both of them, I believe we can trace history and discuss from Plato to Kant, and on the other hand, from the idea of having a space and discussing its deformations.
Yes. There are different, but even Kant's concept on space supported a couple of evolutions, because the basic, even the basic idea, Kant's idea on space, it's that it is an intuition. An intuition in which we frame our sensible data to become knowledge. Later, it evolved because this conception evolved, and he doesn't change his mind, but he give up to this idea. But he's added. New intuition on cosmic space, on absolute space. For example, that God, for example, does not need space and time. So, yes, even Kant's conception of time used to have an evolution, not only between the period from Nicole Oresme to our time. Thank you very much, Professor.
Thank you very much. I really appreciate it. I have to admit, I was not aware of that nuance. I mean, that one escapes me. But that's that's the risk. And should anything go wrong, is Marius's fault, because that's what happens when you invite a geometer in the house.
Claudio, please.
Yes. I wanted to ask you if it really the mathematic of Oresme could be really interpreted as a sort of anticipation of modern mathematics, because I wonder if in his mathematical thinking he did not follow actually the Pythagorean model of understanding mathematics, namely, what does it mean? It means that numbers, equations, and so forth are more or less qualities existing inside things. Now, this is the ancient paradigm that lasted, so to say, until the Renaissance, let's say so. Whereas the modern view of mathematics, I guess, in a way, starting with Kant, is that mathematics is rather something that is independent of things. Therefore, Kant, isn't it, described his pure aesthetics in the way he did, and therefore we can speak thereafter about models, namely something which can match things or not. So actually, mathematics and geometry do not emerge from the things in themselves, as it was in the case of the Pythagorean way of seeing things. This was my question. So can we really speak about an anticipation, or we just project our expectations in that time?
Okay, thank you for this, because it takes a lot of courage for this thought. And if I was alone, I wouldn't dare to say it, but I found it in Dirk Struik. So Dirk Struik taught geometry at MIT, taught history of math at MIT, and he is warning us that in some instances, Nicole Oresme is a precursor of results, and he's providing proofs. In some other instances, he is actually having intuitions, and there is no proof whatsoever, but the statements are true. And by the way, he's also making mistakes. Like I was mentioning the celestial model in the Sphera, like let's don't even discuss that. It's not a Ptolemaic model, it's a novel model that it was very useful to debate astrologers, at least for that. But by the way, Nicole Oresme is making all sorts of other kind of mistakes. Like, for example, and I'm citing, we know everything he ever read. We know that because he's citing it, and we feel that he cited after he read. But there are a couple of instances where we feel that he's citing something that he didn't read. Like, for example, he's saying at some point it was a contribution by George William Coupland, who found a sentence where Oresme said that Plato says the same thing as Ovid. Now, the very fact that you're putting in the same sentence Plato with our Ovid, who ended up his days on the shores of the Black Sea, you don't know. I mean, he read Ovid. He read Ovid because he was a master in the arts, and he learned Ovid by heart. How in the world would you put Plato in the same sentence with Ovid? So, okay, let's be very critical with Oresme. Certain things are amazing, and I think I spoke today only about that. But there are some other things where you're going like, oh my God, what just happened? So what does he know? So think like this. At that time, the greatest bestseller was Isidore of Seville's Etymologies. Now, if nowadays, if you're taking the etymologies line by line, how much of this is still true? Okay, so you have these scholars who have all sorts of information that's actually plain false. And out of all this cultural context, here comes somebody that's just creating a lot of stuff that's true. That's something that he deserves bonus points for that. While in the same time, we keep the critical distance from other parts of his work. That's the story with the precursor. Now about the story with the pure constructions. You're actually right, because the cornerstone of the modernist transformational mathematics is David Hilbert's axiomatic system. And what is the fundamental idea of that construction, which was done, the last version is from 1902. Hilbert wanted to have a pure geometry. So you go ahead and state 20 postulates in the absence of real numbers. So numbers are away, and just based on these 20 axioms, you build geometry. This was something that was born really at the end of the 19th century out of the desire to have a perfect axiomatic system, when people started to notice that Euclid's axiomatic system has 3 very serious flaws. Okay, so the desire of producing a pure axiomatic system could be traced back to the philosophical constructions that preceded the 19th century. It's something that was developed within the German culture, and it was absolutely beneficial for the whole mathematics, and it was something very inspiring. And well, the downside is that you can't really teach it easily. So if you're planning to use Hilbert's axiomatic system and teach it in high school, you won't be happy. So you're going to have to do an axiomatic system where you incorporate the real numbers back, and that's going to be what you may want to do, because Hilbert is difficult. But that's a whole different conversation. Yeah, so it was a very complex take on this, so thank you. Yeah.
Thank you.